Welcome to This Explainer. Today, we're diving deep into logistic regression to see exactly how it solves one of the most fundamental problems in data science, classification. We're going to break down how this incredibly simple, elegant algorithm can take totally chaotic, real-world data and answer complex yes or no questions with absolute mathematical certainty. Let's get started.
So, picture this. We're starting with a massive, real-world problem. Say you're trying to predict whether a tumor is malignant or benign based entirely on its size. If we blindly throw a standard linear regression model at this yes or no question, it's going to spit out unbounded, continuous numbers like 1.7 or negative 0.5. But think about it. What do those numbers actually mean? Is 1.7 very malignant? Is negative 0.5 super benign? No. These outputs mean absolutely nothing in terms of actual probability. Here's our roadmap for the explainer. First, we'll look at why linear regression fails us. Second, we'll introduce the sigmoid solution. Third, we'll tackle binary cross-entropy. Fourth, we'll look at the metrics that matter. And finally, we'll cover scaling up with softmax.
All right, section 1. Why linear regression fails. The broken tool.
It's really wild to see the stark contrast between what linear regression naturally wants to do and what true classification actually needs. Linear regression draws this unbounded straight line that gets easily dragged around by extreme outliers. Think about predicting pass or fail test scores based on how many hours someone studied. If you have one student who somehow studied 50 hours, they'll completely pull and distort that straight line, completely ruining the predictions for everyone else. True classification, on the other hand, strictly needs bounded probabilities. It needs numbers locked exactly between 0 and 1, and a really sharp, resistant decision boundary so it can confidently say yes or no.
Moving right along to section 2, the sigmoid solution, the shapeshifter. To fix that unbounded mess we just talked about, we introduce the shapeshifter of our story, the sigmoid function. You can think of it as a mathematical compactor. It takes literally any wild number, from negative infinity all the way to positive infinity, and squashes it beautifully into the smooth probability curve that sits exactly between 0 and 1. When your input is huge and positive, the output gets incredibly close to 1. When it's a massive negative number, it gets pulled down near 0. It's just the perfect filter.
And honestly, this right here illustrates the pure elegance of logistic regression. Because despite having the word regression in its name, it's absolutely a classification tool, and it operates in 2 brilliantly simple steps. Step 1 is literally just your familiar linear model calculating a score, just your weights times your features plus your bias. Step 2, you immediately take that score and run it through the sigmoid function, instantly magically transforming that raw number into a highly digestible probability. Okay, so the absolutely crucial point here is the decision boundary. Where do we actually draw the line in the sand between a yes and a no? Well, that sharp boundary drops exactly where your linear equation hits 0. Why? Because when your linear output is exactly 0, the sigmoid function spits out a perfect 50-50 coin toss, or 0.5. Everything falling on one side of that line gets classified as a yes, and everything on the other side is a hard no. Which brings us to section 3, binary cross-entropy, the cost of being wrong.
Now, you absolutely cannot use traditional mean-squared error to train this thing. If you do, the sigmoid function is going to create this bumpy, chaotic landscape full of local minima, and your learning algorithm will just get completely stuck. Instead, we use binary cross-entropy. Sure, it sounds super intimidating, but it's really just a brilliant punishment system. It penalizes confident wrong predictions incredibly severely, ensuring our mathematical cost surface stays perfectly smooth and bowl-shaped.
Let's break down exactly why this is so clever. If your model is confident and correct, taking the log of 1 basically gives you 0. The penalty is practically non-existent. The model gets a pat on the back. But man, if your model is confidently wrong, like saying there's absolutely 0% chance of a tumor when there actually is one, taking the log of 0 approaches negative infinity. That creates an undeniable, massive mathematical penalty. And the beauty of this is that it guarantees a perfectly convex surface. It gives us a single global minimum, ensuring that gradient descent will find the absolute best answer for us every single time.
All right, section 4, metrics that matter, the reality check.
Have you ever been totally fooled by a really high test score? Well, if you have a highly imbalanced data set, say something with 95% negative cases and just 5% positive cases, a completely brain-dead model that just blindly guesses negative every single time is going to hit a stellar 95% accuracy. But it completely and utterly fails to do its actual job. In data science, accuracy alone is a very dangerous illusion. To escape that accuracy trap, we rely on the confusion matrix. This is an industry-standard grid that breaks down our specific errors. Instead of just giving us a generic percentage correct, it forces us to look right at our dangerous false positives and our absolutely devastating false negatives. And from that exact grid, we pull the specific metrics we actually need. Precision is your go-to when false alarms are terrible. Think about a spam filter accidentally blocking a super important email from your boss. Recall, on the other hand, is absolutely crucial when missing something could be catastrophic, like failing to detect a real tumor in a cancer screening. And when you really need the best of both worlds, you look to the F1 score, which mathematically balances both metrics perfectly. Now for our final stretch, Section 5, Scaling Up with Softmax, Going Bigger. So what happens when you're dealing with 3, 4, or maybe 10 different categories? A single S-curve just isn't going to cut it anymore. That's where we bring in softmax. Softmax gives every single distinct class its own weight vector, computes a unique score for each one, and then mathematically forces all of those separate scores to become probabilities that add up to exactly 1 or 100%. And to evaluate this upgraded multi-class system, we use categorical cross-entropy. It's essentially an expanded loss function that pairs up with one-hot encoding, which, if you're unfamiliar, is just rows of zeros with a single one marking the true category. It heavily penalizes the model when it misses that one true class. The underlying philosophy here is exactly the same as before. We've literally just leveled the whole thing up. As we wrap up this explainer, I want to leave you with a real puzzle to chew on. Logistic regression, right down at its very core, always produces a strictly linear decision boundary. But we all know the real world is messy. So, when a complex data set completely refuses to be neatly separated by a simple straight line, how are you going to get creative? How will you engineer your features, maybe using polynomial features, to force this linear algorithm to bend to reality? It is a fantastic challenge for you to consider as you step out and actually apply these tools. Thanks so much for diving into the mechanics of classification with me today.